All right, let's look at the sample test for Calculus 3.6 to 3.9 and 1.5. So first off, we need to remember that there are multiple ways to say derivative. Slope of the tangent line, instantaneous velocity, instantaneous rate of change, derivative, y prime, dy dx. Like there are tons of different ways they're going to ask us to do the same thing. We need to recognize it no matter how they ask it. So when they say find the slope of the tangent line, they're just saying find the derivative. So if you're taking the derivative of anything to the 10th power, it's going to be 10 that thing to the 9th power times the derivative of that thing. So 10 that thing to the 9th power times the derivative of that thing. So derivative of x squared plus 5x would be 2x plus 5. So this is the derivative of the outside, and this is the derivative of the inside. We could combine the 10 and the 2x plus 5. So if I distribute that 10, I'm going to get 20x plus 50. And of course, I don't have to distribute the x squared plus 5x. I don't have to multiply it out to the 9th power, and I cannot distribute any of this to it. Order of operations would make me do exponents first. All right, then number 2, instantaneous rate of change, another name for derivative. I want to try to get rid of my quotient here because I don't want to do denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. So instead, I'm going to rewrite this with an exponent. So remember that I've got ln x to the 1 and it's the cube root of that. So that would be ln x to the 1/3. And then to get it out of the denominator to get rid of that fraction, it would be to the negative 1/3. So now the derivative of anything to the negative 1/3 is going to be negative 1/3, that thing, to the negative 4/3, because we're going to say negative 1/3 minus 1, negative 4/3. So here's derivative of the outside. All right, now I need derivative of the inside, so derivative of ln x is 1 over x. So derivative of anything to the negative 1/3 would be negative 1/3, that thing to the negative 4/3 times the derivative of that thing. So we could... excuse me, we could leave our natural log this way, or we could write it moving it back down to the denominator to get rid of the negative exponent and raising it to the 4/3 for that rational exponent. In either case, we've got our negative, and then 1/3 times 1 over x is where we're getting the 1 over 3x. For 3, they ask us to take the derivative of this radical, and remember that you cannot take the derivative of a radical with a quantity under that radical. So we want to try and get that quantity out. So just like we did a second ago, this entire thing is being raised to the 1st power, and then it's the square root of that. So I would rewrite that as cosine t cubed to the 1/2. Now, please notice that it's not cosine to the 3/2. In order for it to be 3/2, this entire thing would have to be raised to the 3rd power. It's just the t that's being raised to the 3rd power. So cosine t cubed, the quantity that's underneath the radical, there's only one of those. So that's to the 1, and then square root gives me a 2 right here. So cosine t cubed to the 1/2. All right, so anything to the 1/2 is going to be 1/2 that thing to the negative 1/2 times the derivative of that thing. So if I want to find the derivative of cosine t cubed, let's just come over here and let's work that as an entirely separate problem. So the derivative of cosine anything is negative sine of that thing times the derivative of that thing. So that would give me negative sine t cubed 3t squared. So that's what we've put right here. So again, the derivative of anything to the 1/2 would be 1/2 that thing to the negative 1/2 times the derivative of that thing. And so here is where we came over here and found the derivative of our inside. So derivative of outside times derivative of inside. We could put our 1/2 times 3t squared together. So you can see that right here. We also had a negative in front of the sign, so that's where this negative is coming from. You could have left this cosine t cubed to the negative 1/2, or you also can write it by putting it back in the denominator and putting it back under the radical. Either one is perfectly fine. All right, then they asked me to find the derivative of tangent of the square root of x to the 5th. So again, I can take the tangent of x, but not the tangent of a quantity. So I'm going to need to rewrite this. So this is x to the 5 halves. So now I have the tangent of x to the 5 halves to make this a little easier to work with. The derivative of tangent anything is going to be secant squared of that thing times the derivative of that thing. So the derivative of x to the 5 halves, just using power rules, so 5 halves x to the 3 halves. So derivative of tangent anything is secant squared that thing times the derivative of that thing. All right, then instantaneous velocity, yet another name for derivative. We have the cosine of the sine of cotangent. Now this is not cosine times sine, it's the cosine of the sine. This is its t value right here. So I'm not multiplying or doing product rule or anything like that. So the derivative of cosine anything is going to be negative sine of that thing. So there's derivative of the outside. Now I need to do derivative of the inside. I need to do the derivative of the sine of cotangent t. So I'm going to come over here and work that as a separate problem. So if I have sine of cotangent t and I'm taking the derivative of that, the derivative of sine anything is cosine of that thing times the derivative of that thing, and the derivative of cotangent is negative cosecant squared. So I can bring that over here, and I've got derivative of the outside times derivative of the inside. So about the only way we could clean that up is we could say a negative times a negative is a positive, but there's not anything else that we can combine there because, again, this is not sine times sine. This is the sine of the sine. If they were being multiplied, it would be sine x times sine x. So again, just the negative times the negative being a positive out in front is really all that I could do with that. All right, for number 6, we have the derivative of secant of 2x squared. So the derivative of secant anything is going to be secant that thing, tangent that thing. So secant 2x squared, tangent x squared, times the derivative of that thing. So the derivative of 2x squared would be 4x. So this is the derivative of the outside, and this is the derivative of the inside. So derivative of secant anything is secant that thing, tangent that thing, times the derivative of that thing. Then for 7, I have cosine x to the 4th. Now another way that they might write that would be like this. That also means that the entire cosine x is being raised to the 4th power. So anything to the 4th power is going to be 4 that thing to the 3rd power times the derivative of that thing. And the derivative of cosine is negative sine. So this is derivative of the outside. This is derivative of the inside. For number 8, again, I need to get rid of my radical. So I'm going to rewrite 2x minus 1 to the 3 halves. So if I have 2x minus 1 to the 3 halves, anything to the 3 halves would be 3 halves that thing to the 1 half, because 3 halves minus 1, 1 half, times the derivative of that thing. So one more time, anything to the 3 halves would be 3 halves that thing to the 1 half times the derivative of that thing. So if we take 3 halves times 2, we're just going to get 3. And you can leave this 2x minus 1 to the 1 half, or you could rewrite it as the square root of 2x minus 1 if you wanted to. All right, for number 9, we're doing implicit differentiation. So remember, we're going to do derivative like normal, but if you take the derivative of y, you have to leave a dy dx in there. So derivative of x to the 4th is just going to be 4x to the 3rd. Here we've got two things being multiplied, so I have to do product rule. I have to do first times derivative of second plus second times derivative of first. So first was x. Second was y, so derivative of y would be 1, but because it was a y, I have to leave a dy dx there. So first times derivative of second plus second times derivative of first, derivative of negative x is negative 1. Then on the other side, derivative of y cubed would be 3y squared, and because it had a y in it, I have to leave a dy dx, and derivative of 4 would be 0. So now I want to get anything that's got a dy dx in it on the left-hand side, everything else on the right-hand side. So this gets subtracted over to the right, this stays where it is. This negative y gets added to the right, and this 3y squared dy dx gets subtracted over to the left. Everything on the left has a dy dx in it, so I'll always be able to factor out a dy dx. So if you put your finger over the dy dx, you can see that what you're left with is negative x minus 3y squared. So to get dy dx by itself, let's divide by that other factor. So we'll divide both sides by the negative x minus 3y squared and answer. Or you could factor a negative out and write it in this way. Either way is perfectly fine. All right, then for number 10, they asked us to find the derivative at a particular point, find the slope of the tangent at a particular point for this problem that we just did. So let's grab this derivative that we had here. We had the 4x cubed minus x over x plus 3y squared, and they want to know what is the slope of the tangent, or the derivative, at the point negative 1, 2. So we're just going to put negative 1 in for x, positive 2 in for y. Negative 1 in for x, positive 2 in for y. And then we're going to simplify, and that gives us negative 6 over 11. They also could ask us to find the equation of the tangent line now that we have a point and a slope. All right, then for number 11, we have implicit differentiation again. So again, I'm going to take the derivative just like normal, but when I take the derivative of y, I have to leave a dy dx in there. So if I take the derivative of cosine anything, it's going to be negative sine of that thing times the derivative of that thing. So the derivative of x is 1, the derivative of y is 1, and I have to leave a dy dx there. On the other side, I have two things being multiplied, so I'm going to do a product. So I'm going to do first times derivative of second, so derivative of sine is cosine, plus second times derivative of first, derivative of y squared is 2y, and we have to leave a dy dx with it. All right, so over here, I've got this negative sine quantity being multiplied by 1 and dy dx. I'm going to need to distribute that. So the negative sine quantity times 1 is negative sine quantity, and the negative sine quantity times dy dx is the negative sine quantity dy dx. And then I want to get everything that has a dy dx with it on the left-hand side and everything else on the right-hand side. So this piece is going to add over to the right. This piece is going to stay on the left. This piece is going to stay on the right. And this piece is going to subtract over to the left. So now I can factor out that dy dx, put your finger over this one and over this one, and you'll be able to see that your other factor is negative sine of the quantity x plus y minus 2y sine x. So let's divide by that other factor, and so that will give us our derivative implicitly. All right, then for number 12, they ask us to find the derivative of the inverse at 8. So they told us that f of x is equal to x cubed, and they want us, g of x is its inverse. So they want us to find the derivative of the inverse at 8. Here's our formula that we've been using for that. So let's put 8 in for a. So let's start on the inside. We need to know what g of 8 is. All right, so I don't know what g of 8 is equal to, but that would be an ordered pair 8 something on the inverse. That means when I'm looking at the original function, x and y switch places. So instead of the point x something, it would be something 8. So if I can figure out where my original function equals 8, that x value then I could fill in, and that would be the same as this value. So again, I'm going to set my function equal to 8. And when I do, I'm going to take the cube root of both sides, and I'll get x is equal to 2. So if this is the 0.28, then this is the 0.82, and so g of 8 is equal to 2. All right, now I want to find the derivative of my original function and plug 2 into it. So we'll come over here, and our original function was x cubed. The derivative of that was 3x squared. And then let's plug 2 in for that. So we would get 2 squared is 4 times 3 is 12. And so since that's 12, that would give us 1/12. Nowhere in there did we find the inverse, take the derivative of it, or plug a value into it. I know this inverse would have been easy to do that with, but a lot of the ones that we work with are not. So we need to use the formula on our test to do this as we did here.